In this lesson, you're going to learn how to discretize data. Discretization transforms data from numeric to nominal data type. There are important effects of discretization, among which smoothing the data, reducing noise, reducing data size, but also enable specific methods downstream to analyze the data using nominal data type. Discretization methods include manual methods, for example, visual distribution analysis. You can imagine this is more suited for small datasets. And automatic methods, which are the ones that we're going to focus on, like binning with equal widths and equal depths binning, regression analysis, cluster analysis, natural partitioning would all be possible methods for discretization. Of course, we are often interested in systematic methods, particularly when you want to deal with big data. So main methods are binning for us, so it's going to be two methods, the equal widths binning and the equal depths binning. For equal widths binning, given a range of values, min, max, we divide in intervals of approximately same widths. Either we set the widths arbitrarily to, for example, W, or we set a desired number of bins to n, in which case W is calculated as W equals max minus min divided by n. Example, if the range of values is 0, 100, and we want 4 bins, each bin will have a width of max minus min, which is 100 minus 0, divided by n, which is 4, 25. So the bins will be 0, 24, 25, 49, 50, 74, and 75, 100. The equal depth binning refers to having the same number of rows in each bin. So given again a range of values min, max, we place approximately the same number of instances in each bin by dividing the total number of samples NB by the desired number of samples in each bin, which is called the depth, D, in which case the number of bins is calculated as n equals NB divided by D. Example, if the range of values is 0, 100 for 100 samples, we want 20 samples in each bin. The number of bins will be 100 divided by 20 equals 5. The bins will be 0, 19, 20, 39, 40, 59, 60, 79, and 80, 100. Each method has its advantages. Equal width binning is more simple. However, it's very sensitive to outliers in the data. The outliers are extreme values that probably correspond to some error. So for example, an age of 300, for example, or even 1 million. It's visible that it's an outlier. But it would be, unless you preprocess and remove the outlier before, that would influence your equal width binning, distort it. Equal depth binning scales well by keeping the distribution of the data. However, the bin values may be more difficult to interpret because generally the intervals will not have the same width. They have the same depth, but if all the points are concentrated in particular close together, then the widths of the intervals will be very different. Now, once you have your bins, you want to smooth your data by replacing the values in a bin by a statistic, such as the average for numeric data. Average of the bin will be the value associated with each row in this bin. The median also can be used for numeric data. And for categorical data, we can use the mode. And this concludes our lesson on discretization.